Okay, guys, we are now needing to work on the chapter 18 material. And hopefully you realize as we're getting a little farther into the semester, this is starting to get to the section where we're in more of the meat. So we're doing more and more actual math and calculations here. And I will remind you, and for those of you who are with us live, I'll remind you that you're welcome to interrupt, ask questions at any time. Just be aware that I'm recording this so that I can post it in the class. I wanted to remind you that even though, notice that it says it's past due, I'm perfectly capable of working on the homework. You have on your schedule that I gave you at the beginning of the semester, in December, it says final math lab homework due date or something like that. You can work on any section. I could go back and work on chapter 3 right now if I wanted to and improve my grade up until that final submission due date, okay? So if you haven't done the chapter 18 yet because you were confused by it, go do it as soon as you watch this recording, or have it up and work it as I'm working this so that you get that material done. And I'll remind you again, as I always do, don't forget to click these things over here so you get those credits as part of the homework grade. And then we're going to dive straight into the questions. So let's see. For each situation, we want each situation described below. We want to identify the population and the sample, explain what P and P hat represent, and tell whether it is appropriate to create a 1 proportion Z interval. Okay. So police set up an auto checkpoint at which drivers are stopped and their cars are inspected for safety problems. All right. So what's the point of doing that, right? We're looking to see the proportion of cars on the road that have certain safety issues. So what's our population? Our population is going to be the cars, all the cars that we're trying to make a generalized result, right? But notice our proportion, our sample is the 113 cars that we've stopped, right? So all cars, I want to estimate the percentage of cars that may be unsafe. So we want to estimate the cars with issues. And then the sample is the cars that are actually stopped at the checkpoint, which is the 113 cars. All right, now what does P represent? P is the referring to the population proportion. So it's going to be the proportion of cars on the road that have some safety violation. So the proportion of all cars with safety problems looks like that would be B. And the P hat refers to the sample that we stopped. So it's saying out of this 113 cars that were stopped, how many have safety problems? So it's the proportion of cars actually seen that have safety problems. So that would be C. Is it appropriate to create a 1 proportion Z interval? All right, so think back about what we said in the lecture. When we're looking at doing analysis with proportions, we needed a few things to be true. Number 1, we needed random sampling. So let me get my annotation going. So number 1, we needed it to be random, right? Number 2 is the 10% condition, which means that our sample size can't exceed 10% of the population. In other words, it can't be too large. And then the third condition is that it needs to be large enough, which for proportions, NP and NQ both have to be at least 10. So those are the 3 things that we're checking each time. So if we look at this, the way the problem's posed, it says police set up an auto checkpoint at which drivers are stopped and their cars are inspected for safety problems. Well, that actually doesn't really tell me anything about like random sampling or anything like that. So to fulfill this, the purpose of the random sampling is that they're supposed to be representative of the population. So I would have to assume that the checkpoint where they're stopped is representative of cars on the road. So in other words, we haven't chosen something really weird. Like if I wanted to estimate the percentage of cars here in Orlando that had safety problem, I wouldn't want to put my checkpoint up in, you know, out in Christmas, right? Because that's not going to be representative of vehicles in Orlando, even though it may still be an Orange County property. Okay, so as long as I assume that they've chosen a reasonable representation of that, that's fine. Now, the 10% condition. Certainly 113 cars is not more than 10% of the total cars on the road. So we're good there. Now the NP and the NQ. So I'm expecting the number of hits that I get here, that's what the NP is representing. N is the number times what we suspect the population proportion to be. Well, I don't know what the population proportion would be, but I know from my sample, I only got 8 hits. That's not 10. So I'm worried a little bit about the randomization condition. I'm not quite hitting that criteria of getting at least 10 successes. So I'm a little bit worried about this. Let's see what our choices down here are. The sample is less, no, B is wrong, right? There are not at least 10 expected successes. This is our expected successes and expected failures. So it's not a simple random sample. It's not the 10 successes and failures. So I'm actually not sure what they want us to choose here. I'm going to try C first, because that seems to be like the most reasonable one, because we only got 8, and that's the biggest issue, because I could assume that if they correctly positioned the checkpoint, that even though it's not randomly sampled, it would still be representative of the population. An online blog puts a poll on its website asking readers to rate the quality of its articles. Of the 507 people who voted, 347 rated the articles very highly. The blog is interested in gauging its users' satisfaction. Identify the population. Well, this is an online blog, so it's going to be viewed by people who read the blog, right? So we want to know about the quality of its articles. So it's going to be the blog's readers would be our population. The sample is the 507 people who voted. Those who voted in the poll. The P represents, again, remember it refers to the population here. So it's the percentage of the population that rated the articles very highly. The proportion of all blog readers, because that's the population, who rate very highly. So B. And then P hat is the sample. So that's the 347 people who rated it highly. The proportion of those who voted in the poll who rated the articles very highly. Is it appropriate to create a 1 proportion Z interval? Okay, so here are 3 conditions again. So let's start with the first one. Is it random? So if I'm looking at this and I'm asking my readers to rate the quality of the articles by voting, am I randomly selecting people to do that? It immediately fails this first condition. So I'm not even going to bother to check the other 2, because I should say it's not appropriate because the sample is biased and non-random. A school is considering requiring students to wear uniforms. The PTA surveys parents' opinions by sending a questionnaire home with 1,082 students. 284 surveys are returned with 160 in favor of the change. Our population is the school's population, right? So the parents of the students at the school is who we're asking to fill out the survey. We were looking to know their opinions. Identify the sample. The sample is the people who sent back the survey, which is the 284 that are returned. What does P represent? I'm trying to get a proportion of the population, so parents at the school, who favor wearing uniforms. Oh, no, parents and students at the school. And then what does the P hat represent? That's on the sample. So that's the proportion of the people who returned the survey who favor the school, of respondents who favor uniforms. Is it appropriate to create a 1 proportion Z interval? So again, these are the 3 conditions that I'm checking. Let's start with the first. If my PTA presents the survey home with the students and it's voluntarily returned, am I meeting that random condition? Probably not, right? Probably only people with a strong opinion are returning the survey. I'm not actually getting the opinion that's representative of people as a whole. So again, I'm not going to even bother to check these last 2 conditions because I know it fails that first one. So it's not appropriate because it is not a simple random sample and there is possible non-response bias. A college admits 1,817 freshmen 1 year, and 4 years later, 1,641 graduate on time. The college wants to estimate the percentage of all their freshman enrollees who graduate on time. Our population is all of the students at the college because we're looking to predict that individual college's graduation rate. Identify the sample. So the sample is this one class, that 1817 freshmen. What does the P represent? That would be the proportion of students at the college who graduate on time. And what does the P hat represent? That's what we got back out of the sample. So the year that we sampled these students, this 1641 out of the 1817 graduated on time. So it's the proportion of that year's students who graduated on time. Can we do our Z intervals? So again, remember, we're checking these 3 conditions. So first of all, is it random? Well, no, right? These are all in the same class year. Maybe something weird like COVID happened that year and that affected graduation rates. We don't know, right? So they do have something in common. They're not independent. So I'm not going to say this condition, that the randomness is satisfied. Now the 10%, certainly the 1817 is less than 10% of all people at the college. And the number of successes, this is greater than 10. The number of failures, this number minus that is greater than 10. So they're both greater than 10. We're good there. Notice how I checked this without knowing the actual P and Q. I just looked at what the survey gave me back. Okay. All right. But I'm still concerned about that randomization. So I'm just going to say it is not appropriate because the sample that says is a simple random sample. Okay, let's read this one. If that year's students are viewed as a representative sample of all possible students at the school, then it's appropriate to create a one. That would be true. If nothing weird happened that year that interfered with the randomization condition, we would be okay to use those as a representation of what happens in a typical year. So as long as that's the case, we'd be fine to proceed. All right, let's clear that now. A catalog sales company promises to deliver orders placed on the internet within 3 days. Follow-up calls to a few randomly selected customers show that 95% confidence interval for the proportion of all orders that arrive on time is 75%. Now this is the P hat value. This is like where the mean would be positioned, the P hat value. Plus or minus, this is our margin of error, okay? So what does this mean? So this means that if I subtract 7% from this and I get to 68%, and I add 7% to the 75 and I get to 82%, right? All right, so that's what we would expect with 95% confidence that our actual mean would lie somewhere in that interval. So no, it is not correct to say between 68 and 82% of orders arrive on time. Because that implies certainty would be our answer there, right? We're saying that it goes exactly that amount, and that's not true. 95% of all random samples of customers will show that 75% of orders arrive on time. No, we're 95%. In other words, that 95% confidence interval is on that boundary between 68 and 82. The actual means somewhere in there. So no, this is not a correct statement. Okay, so much less than 95% of random samples will show that exactly 75% of orders arrive on time. How about none of the random samples will show that exactly 75% of the orders arrive on time? All right, so in other words, this is saying exactly, whereas this is saying yeah, so much less is a broader statement, right? This is saying none of the random samples will show that exactly 75% of the orders arrive on time. That's highly unlikely, but it's certainly going to be less than 95%. 95% of all random samples of customers will show that 68% to 82% of orders arrive on time. Okay, that's the correct idea. This is stated with certainty. And as we know, there's some random varying, but we would expect approximately 95% of all random samples to show that 68 to 82% of orders arrive on time. It's because of the certainty. Oh, I'm sorry, right here. This is saying a result of random samples. It's estimating the population proportion, not the sample proportion. So we're not going to make a statement about what the samples would do. We're making a statement about what the actual proportion, the actual population proportion would be. So in other words, we're saying that interval from 68 to 82%, we're 95% confident that that captures what the true population proportion is, doesn't reflect what the samples will do. One is 95% sure that between 68 and 82% of the orders placed by the sampled customers arrived on time. No, I know exactly what happened to the sampled customers. There's no uncertainty about the sample. The uncertainty is only about the population parameter. So here we go. The statement is not correct. In this sample, we know that 75% of our orders arrived on time. That's how we got that 75% here as the estimate. It's based on the sample, okay? But the uncertainty is whether that reflects the population proportion. There is a 95% chance that on any given day, a customer has a 68 to 82% chance of receiving his package on time. The confidence interval is an interval estimate. Nope, it is not about the sample proportion. It's about the population proportion. The confidence level refers to the probability of the interval containing the population parameter. It is not about what's going to happen on a given day, right? It's saying that overall our population parameter, the number of packages delivered on time, we're 95% confident that that 68 to 82 actually captures Of the 560 samples of seafood purchased from various kinds of food stores in different regions of a country, of 560 samples of seafood purchased, compared to standard gene fragments that can identify the species, 17% were mislabeled. Okay. We want a 99% confidence interval for the proportion of all seafood sold in the country that is mislabeled or misidentified. There are two ways I can do this. I can use my calculator or I can do it by hand. Okay. If I am doing it by hand, we're using the formulas from the chapter 18 material for building that confidence interval. Our confidence interval is that p hat plus or minus the margin of error. And that margin of error, if you recall, and I'll pull up the slide. I'll try to pull up the slide. There we go. Right here. Our margin of error is that critical z-value times the standard error, okay? So for us, that critical z-value goes with the 99% confidence. So I'm going to go back to my slides here and notice that for, I thought I gave them to you. I might have given it to you in chapter 17. Okay, I don't remember where I gave it to you, but somewhere I gave you a list of the critical Z's and the confidence interval link that goes with it. So maybe that's in an upcoming chapter. I'll show you how to get it, okay? So what I'm doing here is I'm saying with a normal distribution, the confidence interval being 99%, means that I'd expect the 0.99 in here. So I'm looking for the Z value that's here and here. The positive and negative would be the same. It's symmetric, right? That leaves 0.99 in the center. So if 0.99 is in the center, then that means that 0.01 is split on the outside. So half of 0.01 goes here. 0.01 divided by 2, that's 0.005. And that, by symmetry, the same amount is here. So I want to know what that Z critical is. So the way that I would do that is I would either use my calculator or look it up in a chart. And I'll show you very quickly how to do both of those if I can get a chart. So I'm going to pause for just a second so I can pull up a chart. And my tables are here. This Z table should work. Okay, so let's resume the share. Okay, there we go. All right, so you can see I've pulled up a chart here. So I'm looking for where I have 0.005 in the center, and it looks like that would be right about here-ish. And the Z-score that goes with that is negative 2.5, and then in between 7 and 8. So maybe negative 2.575, something like that. That's how I would use a table to get it. The way that I would use my calculator is I would go second and the distribution and do that inverse norm. And the area on the left is that 0.005. It's a Z-score that I'm looking for. So the mean is 0 and the standard deviation is 1. And that's the area on the left. And we get the negative 2.576. Basically the same thing we read in the chart, just a little more exact. Okay, so negative 2.576. So where am I? Here we are. So I go, my Z star here is negative 2.576. Times the standard error. Now that standard error, I showed you that formula here, is that square root of P P hat times Q hat over N. So I'm going to go square root of P hat. Q hat is 1 minus P hat over the N. Okay, so for us, the P hat is the 0.17. We're going to go 0.17 plus or minus -2.576 times the square root of 0.17. 1 minus 0.17 would be 0.83 over the N is the 560 samples. All right, so now I've pretty much got to put that in the calculator. So I would go 0.17 minus negative 2.576 times the square root of 0.17 times 0.83 divided by 560. And that's my lower bound. And then to get the upper bound, we just do the same thing, but we're going to change that minus to a plus. And we see our confidence interval is 0.1. How many decimals did they want? 1 decimal place. So 0.1 to 0.2. Oh, they want it as a percentage. Okay, so 12.9 to 21.1. Okay, look how much work I did to figure that out, right? Using those formulas, that was a pain. Now, I could have done the whole thing on my calculator without using those formulas at all. So before we enter that, I'm going to show you how to do that now. So on your calculator, you're going to hit second. No, you're not. You're going to hit just the step. Oops, I did it again. Okay, so our stat key, and go over to tests. And my Z interval is what I'm looking. Hey, go back. My Z interval is what I'm looking for here. Actually, I think I want a 1 proportion Z interval. Where is that? There it is. 1 proportion Z interval. So option A here is my 1 proportion Z interval. And my X, well, that 17% of 560 was the successes I got. So I'll go 0.17 times 560, and that's 95.2. We're going to call that 95 because you can't have 0.2 of something, 0.2 of somebody having gene fragments, or 0.2 of something being mislabeled. The N is 560. And my confidence level is 99%. And there's that same interval, 0.129 to 0.211. Excuse me. So I could have just done it straight on the calculator, not use the formulas at all. All right, what does this confidence interval say about seafood sold in the country? Excuse me. All right, so there's not a chance that the true proportion is in the interval. The true proportion is either in the interval or not. All right, it's whether that, the chance is whether that interval captures it. All right, this is not about the samples. We are 99% confident that the interval captures the true proportion of all seafood sold in the country that is mislabeled. This is the accurate statement there, because there's no chance about where that true proportion lies. And it's not about the samples that we're making a statement. We're making a statement about the population proportion. Is the government spokesperson's criticism valid? What was that? A government spokesperson claimed that the sample size was too small relative to the billions of pieces of seafood sold each year. So I got back 17% of 560 is bigger than 10. So my number of successes is bigger than 10. My number of failures is bigger than 10. And this is 560 is less than 10% of all fish out there. And so as long as this is randomly sampled, we're good. So no, as long as the necessary assumptions and conditions were met, our results can be generalized. A poll taken this year asked 1,040 adults whether they were fans of a particular sport, and 0.41 said they were. Last year, 0.4 of a similar size sample had reported being fans of the sport. Find the margin of error for this poll taken this year if one wants to construct a 95% confidence interval. All right, so that margin of error, remember, is, I'm again going to show you two ways to do it, your calculator and the formula. So that margin of error is what we're adding and subtracting to the p-hat. So it's the z star times our standard error, right? So that z star for 95% is that 1.96, and the way that we get that and by the way, on the previous problem that I did, I left the negative on the z star, and I shouldn't have done that. I mean, it doesn't matter. We just flip the bounds of the confidence interval. But usually the z star, we just drop the negative, okay? This is the negative z star. This is the positive z star. It's 95%, so that means the 0.95 is in the middle. So I'm splitting 0.025 over here, half of the remaining 0.05, right? 1 minus 0.95 is 0.05. Divide it by 2, and that's the area that goes there. And that by symmetry, the same thing here, 0.025. So I'm getting that 1.96 by going to my calculator and doing second distribution, inverse norm, plug in the area that's here to find this z value. And it's 0.025. It's a z-score, so the mean should be 0 and the standard deviation should be 1. And there we see this 1.96. But notice that every time it's 95% confident, it's going to be that 1.96. It never changes. So we use that one so much, it's just worth remembering that's 1.96, okay? All right, so it's 1.96, then times the square root of the p-hat, which 0.41 times 1 minus 0.41. 1 minus 0.41 would be 0.59, I think, over the number in the sample, 1040. Okay, so I plug that into my calculator, and that's my margin of error. So I would go 1.96 times the square root of 0.41 times 0.59 divided by 1040. Now, the other way I could have gotten that margin of error is I could actually calculate, just using my calculator. I wouldn't do any of this formula stuff that I did here. Go to stat and go over to test and go to option A to get that one proportion z interval again. Plug in my data. So 1040 times 0.41 is what we got. Is 426.4. I can't have 0.4 of a person, so we'll call that 426 out of the 1040. And this time I want a 95% confidence level. And notice that it generates this confidence interval for me. Well, my margin of error is half the distance of the confidence interval. So I'm going to draw this out for you so you understand what I'm saying here. I'm going to try to draw it out for you. See this 0.37, so we'll call that 0.38. 0.38 is here on the number line, and 0.44 is here on the number line. Directly in the middle is the p-hat value. So I get the middle by averaging those two, right? So I could take, or equivalently, I'll show you, either way, 0.37, oh, it went away. I lost my numbers and I didn't write it down. I wanted to show you that it was the same. So let me do this. So let me pull that back up. This was where we calculated it by hand, right? Using the formulas, and we got 0.0298, round to 3 decimal places. So, all right, I'm confused on this because they listed these as percentages and I don't see the percentage sign after this. So I'm going to type it in as the decimal and we may have to change it to percentage. 0.0298 would round to 0.030. In case it's percentages. I'm going to go ahead and check the answer and okay, good. All right, 0.030. All right, that's the way they wanted it. But we're not moving on to the second part yet because I was trying to show you how to get it from your calculator. Okay, so remember what I did here is I went second distribution and, oh no, I didn't. I went stats, I went stat test, I went down to option A and ran my 1 proportion Z interval. We filled in the data and it gave me these values. Okay, so that I graphed it on a number line. So now this total distance that's here is the margin of error this way and the margin of error this way. So it's 2 times the margin of error. So if I subtract these 2 values and then divide by 2, that'll also give me the margin of error. All right, so let's subtract them because notice it goes away if I type into my calculator. So I'll do it over here. 0.37973 and 0.4395, I think is what we're looking at. All right, 0.4395. So I need a 0, 4, 10, 7, and 8, 14, 7, and 2, 18, 9, and 3, 12, 5, 0, point. All right, so 0.05977. So if I take 0.05977, calculator, 0.05977. That didn't work. Try it one more time. 0.05977. And I divide by 2. That should match what we got by doing the formula here. And we rounded to 0.030, but notice it's the same, 0.02988. That was what we rounded. That's what we got using the formula. Now, notice that if I add that to the point, to this bottom number, so if I go this plus the 0.37973, that should take me to the 0.41 that's in the middle here, right? That's my sample proportion is where we're centering it. This is the 0.41. So I could have just subtracted 0.44 minus 0.41 and gotten the same thing, right? I just carried the decimals with me. Okay, a lot of explanation to show you something we already worked out quite quickly and easily. All right, explain what the margin of error means. So that's how far away from, right, that actual sample proportion we got, right? So let's see what these sentences say. One is 95% confident that the sample proportion, no, we know exactly where the sample proportion is. So there's no confidence on the sample proportion. So I can rule out A immediately. In 95% of samples of adults, the proportions who are fans of the sport will be within within the plus or minus the margin of error of the sample proportion. No, no, the statement is not about the samples. Okay, one is 95% plus or minus margin of error confident that the true proportion of adults who are fans of the sport is equal to the sample proportion. It's not equal to the sample proportion. No. There's a 95% chance that the true proportion of adults who are fans of the sport, there's no chance on the proportion. So this is the closest statement. And 95% of samples of adults. So if we were to run this 100 times, we would expect 95% of the samples to be within one margin of error of the sample proportion. Yeah, okay. So I thought we were not making a statement about samples, but I didn't see another correct one here. So let me read it again and see what I missed. Oh, I'm sorry. I stopped reading A too soon. Okay, one is 95% confident that this sample proportion is within 95. I thought it was making a statement about where that sample proportion lay, and that would be wrong. But it's saying this sample proportion is in with one margin of error of the true proportion, and that's true, right? We're saying we're 95% confident that between this value and this value captures where the true proportion lies. So my mistake, I just didn't read the first sentence well enough. All right. If one wanted to be 99% confident instead of 95% confident, would the margin of error be larger or smaller? Look at that formula. See, I'm multiplying the Z star. The bigger the confidence level, the bigger that number is. So it's going to make the interval wider. So the more confident I am, the wider the interval. To be more confident, the interval needs to contain the true proportion more often. So the margin of error would be larger. That seems like a correct statement. Let me make sure I'm not making a mistake. No, that's not true. That's not true. Okay, so we're good. Find the margin of error for the poll taken this year if one wants 99% confidence in the estimate of the percentage of adults who are fans of the sport. Okay, so we can do this quickly on our calculator. So second, no second. I just want the stats key. Stats, test, go down to A. Stats, test, go down to A. And we're doing 426 out of 1040, but we're changing this confidence to 99%. Calculate it. So I can go 0.44889 minus 0.41, where we know it's centered, to get that margin of error in the diagram I showed you before, 0.03889. So 3 decimal places, 0.039 is what we're going to call And by the way, I could have done it like I did the previous problem and used the formulas. I'm trying to show you that you're doing the same thing. You can just use technology to help you go a little faster. In general, if all other aspects of the situation remain the same, will smaller margins of error produce greater or less confidence? Smaller margins of error will give you less confidence in the interval. Philanthropic organizations send free mailing labels and greeting cards to a random sample of 100,000 potential donors on their mailing list and receive 5,067 donations. Okay, let's do it. So stat tests, go down to the one. By the way, I could do this with the formulas like I did the previous problems. We received 5067 out of 100,000. And I wanted a what confidence? 99. Oh, whoops. And I just made it go away. Try that again. Okay. So it's going to be point. All right. So this is in percentage. So I'm going to move the decimal point over to 4.89 and 5.25. Given the confidence interval you found, is the proposed rate? Yes, it's inside that interval. So, yep, we're good. A poll found that 56% of a sample of 1,000 teens in a certain city, country go online several times a day. Find the margin of error for this poll if we want a 95% confidence. Okay, again, I can use the formula, but I'm just going to go stat tests down to the A. I'm doing 0.56 of 1,000, 560, and then it's out of 1,000, and I wanted a 95% confidence level. All right, so notice we get 0.59077. So I'm just going to subtract 0.56 from it because I'm going to remind you again what I'm doing here. This interval is saying here's the 0.52923. Here's the 0.59077. The mean is in the middle, the 0.56. This is one margin of error. This is the other margin of error, that length. So all I have to do is take this and subtract 0.56, and that gives me the margin of error, right? That would be the result of that subtraction. So that would be 0.03077. All right, so that would be 3.1 because it's to one decimal place. So 3.1. Explain what the margin of error means. Okay. All right, there's no chance related to the teens. The percent of teens in the country go online several times a day within. All right, so this one seems pretty good. Let me see. Okay, it's 95% of the samples of teens in the country, the percent who go online several times a day will be within 3.1% of the estimated 56%. Oh, wait. Here we go. The pollsters are 95% confident that the true percent of teens in the country who go online several times a day. All right, because we're trying to estimate the true percent are within 3.1% of the 56% that we found in the sample. Okay, there we go. If instead we need to be 99% confident, all right, we're increasing the confidence level, so that's going to make the margin of error bigger. Since a larger degree of certainty implied by the new confidence level requires an interval with less precision. That's a strange way of saying, if I make my margin of error bigger, right? If I make the margin of error, if I'm casting a wider net, I've got to do it with a larger interval, right? So it's not going to be as tight around the estimate. It's going to be wider. Okay. Find that margin of error. Oh, they just want us to change this to 99%. So stat tests option A. Same, change to 99. And so I'm taking 0.60043. And I am subtracting my estimate 0.56. 0.04043. So that would be 4, I'm going to 1 decimal place. So 4.0. In general, if all other aspects of the situation remain the same, would larger samples produce smaller or larger margins of error? Look at this is my margin of error right here. See this? This is the critical Z times this formula. Look at where the sample size is. It's in the denominator of the fraction. If I have a fraction and I make the denominator larger, that makes the fraction smaller. So if the fraction's smaller and I multiply by something, that makes that margin of error smaller. Increasing my sample size will make the margin of error smaller. The standard error to be smaller. That's what I meant by that fraction is smaller, right? The critical value is the Z star. Notice it doesn't affect the Z star. That's the critical value. It's only making the standard error smaller. The mayor of a small city has suggested that the state locate a new prison there, arguing that the construction project and resulting jobs will be good for local economy. A total of 183 residents show up for a public hearing on the proposal, and a show of hands finds 31 in favor of the prison project. What can the city council conclude about public support for the mayor's initiative? I would say they can't conclude anything. Okay. Yeah, that's the most reasonable answer because they're showing up voluntarily. They probably have strong opinions on the matter, right? A city ballot includes a local initiative that would legalize gambling. The issue is hotly contested and two groups decide to construct polls to predict the outcome. The local newspaper finds 47% of 1,400 randomly selected voters plan to vote yes, while college statistics class finds 46% of 400 randomly selected voters in support. Both groups will create a 95% confidence interval. Assume all voters know how they intend to vote and that the initiative requires a majority vote to pass. Without finding the confidence intervals, explain which one will have the larger margin of error. This has a larger sample, this has a smaller sample size, so it will have a larger margin of error. The bigger the sample size, the smaller the margin of error. So our statistics class will have a larger margin of error because it has a much smaller sample size. Find both confidence intervals. Okay, so for the local newspaper, keep hitting second. Okay, stats, tests, A. We're doing 47% of 1,400. Out of 1,400. And we're doing it with a 95% confidence. So we're at 0.44. Let's move this over. 0.44386. I'm doing to 1 decimal place. I want to go 44.4 to 49.6. And for the statistics class, we're going to go stat test option A. And they're doing 46% of 400. Out of 400. And it's again a 95% confidence. So we're going to go 41.1 to 50.9. Which group concludes that the outcome is too close to call? These guys have 50% in their interval. These don't. So in the newspaper is going to say it won't pass because it doesn't get to a majority. It doesn't get over 50%, so it can't get a majority vote. The statistics class, though, 50% is a reasonable value. Contains 50%. Vitamin D, whether ingested as a dietary supplement or produced naturally when sunlight falls upon the skin, is essential for strong, healthy bones. Bone disease rickets was largely eliminated in the 1950s, but now there's a concern that a generation of children more likely to watch TV or play computer games and spend time outdoors is at increased risk. Okay, a recent study of 3,000 children randomly selected found 19% of them deficient in vitamin D. Stat tests. Option A. Okay, so we're doing 3,000 times 0.19 out of 3,000. And this is a 98% confidence. So 0.173 and 0.207. Oh, I didn't look at the confident conditions. Haha. let's double check and make sure that they're okay. A recent study of 3,000 children randomly selected. Okay, so we've got the randomization. 3,000 is certainly less than 10% of all children, so we're good there. And 19% of 3,000 is bigger than 10. And then the remaining, what is that? 81% times 3,000 is also bigger than 10. So all of my conditions are satisfied. That's fine. So we got our confidence interval. Explain carefully what the interval means. Oh, we are 98% confident. No, wait. All right, so here we are 98% confident that the proportion of vitamin D deficiency in a randomly sampled child, this isn't about a single child, right? The 98% confident that the proportion of people falls inside the confidence interval. Well, this isn't about all people, it's about children. So that's the third statement. 98% confident that the proportion of children deficient in vitamin D is 0.9. This is not about this, the value we got back from the sample. That's why we did bounds on it, right? Explain what 98% confident means. Okay, so if we were to do this 100 times, 98% of them will capture the true population proportion. Confidence intervals that contain the true proportion of children that are deficient in vitamin D. In 2004, it was reported that 73% of 1,636 randomly selected college freshmen returned to college next year. The study was stratified by type of college, public or private. The retention rates were 70.6 among 512 in public, 74.3 in private. Will the 95% confidence interval for the true national retention rate in private colleges be wider or narrower than public? Okay, private had 1124. Public had 502. This sample size is bigger, so it will produce the smaller interval. So private will be smaller because the sample for private colleges is larger than for public, and because the what? Okay, so I need to make a statement about retention rates as well, is what this is saying. My retention rate is 70.6. Well, the retention rate, though, is further from 0.5. Yeah. And that's a true statement. It is, so the distance is also farther away. So I hate that I'm recording this right now because it's caught me on this, why it matters that it's away from 0.5. And I'm trying to think for just a second as to how that's affecting it, because the sample size definitely affects the width. But it's saying, if it were just pure chance alone, that would be at the 50% mark. So the further I am from the 50%, well, let's check it, but I apologize. I'm going to have to think a little bit more why that retention rate's making a difference there. That second part of the question is not coming immediately to my mind as to why that's affecting the width of the confidence interval. The sample size certainly is. So if I think of that, I'll come back to it in a moment. All right, so do you expect the margin of error for the overall retention rate to be larger or smaller than the margin of error for the retention rate in public colleges? Okay, so look at what's going on here. In public colleges, it's smaller than the private colleges. So I would expect this to pull it up a little bit. So I would expect it to be higher, right? Oh, so the margin of error for all of them. Well, I would assume that if it's stratified by type of college, then this percentage was getting, oh, it's right here. It is the 1636, the combination of these two. So this is going to have a smaller margin of error because the sample size is larger there. So the margin of error for the overall retention rate should be smaller since the overall sample is bigger. And since the overall retention rate, 73%, is closer to the 75. For public colleges. The overall retention rate is closer to 0.5 than 70.6. That's not true. Why are you marking? That question is a little frustrating. It's the first time I've really paid attention to that question. I got to come back to that one. Sorry, guys. But that distance from the 0.5, that second statement did not seem correct to me to say that because it wasn't closer to 0.5 than the overall retention rate. But we're going to just move on for right now. And like I said, if it occurs to me what it is that is going on there, I'll come back to that. All right. Wildlife biologists inspect 137 deer taken by hunters and find 29 of them carrying ticks that test positive for Lyme disease. 90% confidence. So let's go stat, tests, and go down to A. All right, so we're doing 29 out of 137. And by the way, every single time I'm doing this, I'm checking my 3 conditions. I'm checking to make sure that it is randomly selected. Well, we don't have that, but we would hope that these represent usual deer, right? Nothing unusual about them. 10%, 137 is My apologies on that. These are our problems with technologies these days. Unfortunately, I had my laptop unplugged and you touch it wrong and it reboots. And so I have plugged it in. I forget about making that mistake sometimes. So I'm getting right back to where we were. Trying to pull up everything, guys, and I apologize because I know it's recording, but all right, so let's go back to sharing the screen. Hopefully this will all come up pretty quickly here. I'm glad you guys didn't leave, otherwise it would have closed out this presentation. All right, perfect. And I'm going to pause that just for a second so that I can move that to a more convenient location on the screen over to my left. Okay, now let's go back to sharing the screen. Okay, there we go. All righty. So didn't we do this one? We were where? Let's see, on the left. Okay, there we go. All right, so what I was saying is we check the randomization. They have to be representative of the population. 134 is less than 10% of all deer, and this is bigger than 10, and the failures, 134 minus 25 is bigger than 10, so all of our conditions are satisfied. Stat, tests, go down to A. And I am plugging in 25 out of 134 with a 90% confidence, and we get 0.1, so 13.1 to 24.2. If the scientists want to cut the margin of error in half, oh, okay. Let's go back to that formula for a minute, which I no longer have up. Let me pause that sharing just a moment so that I can bring back up that formula, because I need to explain to you why it's happening the way it's happening. So I'm getting into, this was chapter 18, I think is where it is. Okay, so let's share again, resume that share. Okay, so a little bit bigger. No, well, that's okay. We'll just work with it on. Okay, see right here. I want to get a larger, what did it say? A larger, I want the margin of error to be cut in half. So if I want the margin of error to be cut in half, I want a 1/2 here. Well, it would have to come from here. If I've got a 1/2 in front there, let me try to write on this. If I have a 1/2 in front of a square root, to take it inside the square root, I'd have to square it for it to stay a 1/2. So it would come in as a 1/4. So it would be 4 times the sample size. So in order for me to cut the margin of error in half, I must do 4 times 134. So 134 times 4 would be 536. What concerns you about this sample? Okay. I don't know if that's a true statement or not, but I assume if they're saying it, maybe that is true, that female and young aren't hunted. Okay. So C might be a reasonable thing to suspect. We don't have, the ones that they hunt may not be representative of all deer in the population. Editors preparing a report on the economy are trying to estimate the percentage of businesses that plan to hire additional employees in the next 60 days. They are willing to accept a margin of error of 3%, but want 90% confidence. How many randomly okay, so I showed you here how to get your sample size. All right, so look at this. We need the Z star that goes with 90% confidence. So let me draw it out for you. That means this is a Z-score, so mean is 0, standard deviation of 1, but 90% confidence means that in between these values, the 0.9 is here. So 1 minus 0.9 or 0.1 is split evenly on the outsides. So half of 0.1 makes 0.05 here and 0.05 here. Let's find it. So we're going to go to our calculator and we're going to go second distribution. Try that again, second distribution. Inverse norm, we want the 0.05. Mean is 0, standard deviation of 1, that's fine. Paste, that's fine. We get 1.645. So my critical Z is 1.645. All right, let's see what else we need here. So that goes here in the formula. Then I need the P hat, Q hat, and then over the margin of error squared. All right, so we're going to have 1.645 times P hat. I don't have a P hat. So since I don't have a P hat, I'm going to use 0.5, 50% as the estimate, point estimate, right? So 1 minus 50% would be 0.5 over 3%. Oh, and so this one was squared, and the 0.3 is also squared according to our formula here, right? See how this is squared and this is squared, but P hat and Q hat are not. All right, so I'm just going to type this directly into my calculator. So we're going to go 1.645 squared times 0.5 times 0.5, and then divide that by 0.03 squared. That's 752. Reaching out two standard errors on either side of the sample proportion makes us, okay, so remember that our 68, 99, the empirical rule says within one standard deviation. So this is -1 to 1, right? 68% is in here. And then 2 standard deviations is 95%. And then 3 standard deviations is the 99.7%. That's our empirical rule, right? So if I go 2 standard errors on either side, it's about 95%. We know it's not actually 2, it's actually that 1.96. But according to our empirical rule, right, we can estimate that with like a 2. In a confidence interval, the amount we reach out on either side of the sample proportion is called the margin of error, right? That's, remember what we're doing here is we're saying this is my P hat. And from the P hat, I'm going 1 margin of error this way and 1 margin of error this way. And that gives me the confidence interval that we hope contains the true population proportion, or where whatever confidence level would contain it, right? Which of these statements correctly interprets what it means to be 95% confident? No, the sample proportion's in the middle of the interval. We're building it around it. 95% of the samples we construct will produce confidence intervals that capture the true population proportion. If the margin of error increases, the confidence interval gets wider, right? Because think of that picture that I just drew right here, right? This is p hat. This is one margin of error this way. This is one margin of error this way. That forms the confidence interval. So if the margin of error is bigger, then the confidence interval is wider. If the level of confidence increases, go back here. See, this is my margin of error right here. So if this gets bigger, then the interval gets wider because I'm multiplying by a bigger number. Again, I can be more confident when I cast a wider net. A smaller net generally means less confident. If the margin of error decreases and the sample size remains the same, okay, so my margin of error decreases, but the sample size remains the same. So this value remains the same, this value remains the same, but this decreases, this had to get smaller. So my critical value, which is related to the confidence level, drops. To decrease the margin of error without decreasing the confidence level, the sample size, okay, remember what we said, sample size gets bigger, margin of error goes down. So the sample size needs to be increased. All right, guys, this should allow you to complete the homework. If you still have questions on some of the stuff that I talked about, be sure to let me know. I'm gonna go ahead and stop recording now, but then I'll ask if you have any questions. So where's my, uh-oh. There we go. Now I can stop.